This week, we will cover more detailed aspects about MIDI and MIDI data. This week's content will focus on defining the essential elements of MIDI data and what it consists of, understanding terminology associated with MIDI data and how it is used, and we will discuss the many applications and uses of MIDI data. As we discussed in week 11, we use MIDI to interact with a computer in a musical way. We use MIDI connections and data streams to control a DAW or other MIDI-compatible music equipment. Since MIDI is control data and not digital audio, we now need to understand how MIDI data works in detail. Understanding what MIDI data consists of allows us to better use a sequencer and MIDI controllers to make quality musical sequences. There is a wide variety of MIDI controllers available. Last week we discussed MIDI controllers in general, but many are designed to look and feel like musical instruments. Some are designed to be a series of pads and sliders. Some are meant to be keyboards like a piano keyboard. The most common type of MIDI controller is the piano keyboard, but even those often come with pads, sliders, and knobs that are actually MIDI controllers. Regardless of the design, all MIDI controllers are meant to allow humans to musically interact with or perform with software instruments. Although the most common MIDI controller is the keyboard controller, there are others. At the top we have the iwi wind controller. The wind controller acts like a woodwind instrument and allows us to use breath pressure and breath control to provide a sense of nuance and performance. The DJ or turntable controller uses two turntable-like controllers to control the performance of wave files and other elements on screen, as well as other pads and sliders that you can map to different filters and other parts of a DAW. We have, of course, the grid or pad controller on the bottom right, which has a series of assignable pads. Those pads can mimic a keyboard controller as well by giving us whole and half step patterns, or they can be set to control certain clips and the triggering of certain events on screen. At the bottom left, we have a drum controller, which is a smart device for using your fingers or a drum a drum stick or mallet to control sounds. They are pressure sensitive, and even the rim and other quadrants of the pad can be linked to different things on screen. And there are many others. All of these MIDI controllers, regardless of the type, rely on MIDI messages. MIDI messages are digital signals that instruct a MIDI-compatible device on how to perform a musical action. When we press a key or a pad, we turn a knob or move a slider or perform any MIDI action on a MIDI controller, it sends a MIDI message, usually via USB cable, to the digital device it is connected to. All MIDI messages have a data range from 0 to 127, providing 128 values in which to control different parameters. MIDI messages are categorized into three types. There are note messages, continuous control messages, and program messages. These days, the first two are what we use most often, and therefore we will not really talk about program messages at this time. MIDI note messages are typically transmitted by keys or pads, and are the majority of MIDI messages in general. When we play a piano key or press a drum pad on a MIDI controller, a MIDI note message is sent to the computer. When we play a sequence in a DAW, it in turn sends MIDI note messages to a software instrument. MIDI note messages consist of four main parts. Although there are more, we will focus on these four values: note on, note number, velocity value, and note off. Since MIDI is control data, all of these values have a numeric value between 0 and 127. The MIDI note number is an integer between 0 and 127 that represents a note's pitch. Computers do not understand traditional notation. They do not understand necessarily what a C sharp or a B flat is. Therefore, it must be translated into a number of some sort. The data range from 0 to 127 provides 128 values, which exceeds the range of a standard piano, which has famously 88 keys. Therefore, we have a MIDI note number for all the piano keys and beyond. We can think of it this way. Middle C has been assigned the number 60, which is roughly in the middle of the spectrum there. If middle C is 60, then each key has its own number. So if the key, the half step above C, C sharp, or D flat, is 61, the D above middle C is 62, and so on and so forth. Each key gets its own number, regardless of its accidental or enharmonic value. Since each octave adds 12 half steps, we add 12 numbers to our value to find the octave above. So for C4, or middle C, if C4 is MIDI number 60, then the octave above that is going to have plus 12, or 72 for C5. Conversely, if we go down an octave from C4, we go to C3, or we subtract 12 from 60 to get to 48. This method provides a distinct number to every note that we use in the equal tempered system. In regard to dynamics, we refer to MIDI velocity values. MIDI velocity is a MIDI parameter that refers to how fast a key or pad is pressed on a MIDI keyboard. When we press a key on a piano very quickly or hard, it changes not only the loudness or the volume, but also the timbre, or how hard the hammer of a piano strikes a string. That changes both volume and timbre at the same time. Therefore, the concept of velocity covers two things at once. It covers volume and timbre of a sound. This combination of volume and timbre is best expressed in the MIDI realm as velocity. We can make a MIDI sequence sound more realistic by working with its velocity contour. The chart on the right shows us a list of common music dynamic markings, from pianissimo to piano, mezzo piano, mezzo forte, forte, fortissimo, and fortissimo. Generally, these reflect from very soft to very loud. The velocity numbers associated with these values is a rough estimate, but generally we can understand that your loudest value will be 127, or fortissimo. The middle of that spectrum is around 64, or mezzo piano. The quietest dynamic is only 16 velocity value. And of course, if the velocity value was 0, that would mean that there is no sound. We can control the velocity of each note we program in a DAW. Down at the bottom, we see a view from Ableton and its velocity contouring. Usually that is shown below or in connection with the MIDI note values on screen. Next, we can talk about the continuous controller messages associated with the MIDI protocol. Most controllers, even keyboard controllers, have more than just note entry modules on them. Continuous controller messages transmit a range of values from 0 to 127 to control a variety of parameters that isn't just on or off, or one value and then 0 value. Continuous controllers imply a continuous change, something flexible. Of course, there are 127 possible CC messages. Here is a list of common CC controllers and their assigned numbers. The most common, found on most devices, is the pitch bend and mod wheels on the left side of most MIDI keyboard controllers. Those are also found on most digital synthesizers, even dating back to the Yamaha DX7 in the mid-1980s. The modulation wheel on the left is CC1. If we turn or move the modulation wheel, and CC1 will be sent, the modulation wheel will trigger a continuous controller message to change as we move the wheel. So if we move it up, it will give us a CC message that continuously moves upward in number. If we move it down, it'll generate MIDI CC numbers to go down a number. Each continuous control parameter is assigned to each device. So our modulation wheel has a number, CC1. Our expression or pitch bend is CC11. Most electric pianos or MIDI pianos have a sustain pedal or a damper pedal that is pictured here. These are very common and plug in with this 1/4 inch plug. But what they do is they respond to the positioning, either up or down, send a voltage to your MIDI piano. That MIDI piano then changes the CC number associated with the CC number 64. Lots of different continuous controller message options are out there. These are the most common. Sometimes there is a data entry slider on your keyboard controller. Sometimes there is a volume pedal or otherwise another kind of volume control. Sometimes there is a panning function. So these are options that can be attached to your MIDI controller and the CC numbers that they are associated with. The CC2 for breath controller, remember, applies best to the iwi wind controller that looks like a woodwind, for instance. When we record or program a MIDI sequence, all of these note values and CC values are recorded by the DAW into a MIDI sequence. The graphical user interface, or GUI, of the sequencer allows us to edit and see any of these MIDI values in time. MIDI sequencers typically rely upon a tempo. Most MIDI sequences are tempo-driven. It is important to set the tempo, or beats per minute, when creating a MIDI sequence. A tempo grid is a visual representation of the tempo and meter of a sequence. The tempo grid resolution is extremely important as well, as it shows us the beat values per grid line according to tempo and meter chosen. So for instance, our tempo grid resolution can be simply 1/4 notes, half notes, 16th notes, or 32nd notes, depending on the setting that we choose down here on the left. The term quantizing, in general, refers to the assignment of a value to an event. In the realm of MIDI sequencing, MIDI quantizing is a process that assigns MIDI notes to a tempo grid to correct rhythmic issues. It's a great way to make your MIDI sequence sound like it's connected with other layers in the tempo grid. We use quantizing to sequence, or to synchronize different musical layers. If MIDI quantizing is enabled, the sequencer will adjust MIDI notes to begin and perhaps end at the nearest point in the tempo grid. Sometimes when we play MIDI information via a MIDI controller into a MIDI sequencer, we don't always arrive on the beat. What quantizing does is it shifts all of those note values to different points in the tempo grid to correct it. Quantizing is an important way to correct rhythmic errors in a sequence and to assure that everything aligns to a common tempo and meter. Now is a great time to talk about MIDI 2.0. In February 2020, a new generation of MIDI was released. MIDI 2.0 is an updated next-generation MIDI protocol that was released. And with it was released a series of controllers that rely upon new ways and options for generating expressive performance. MIDI 2.0 is a product of an age in which computers and controllers are more sophisticated, powerful, and quick, and can respond and generate MIDI information at a fast in a fast and efficient way. MIDI 2.0 features two-way communication between electronic musical instruments and controllers, MIDI capability inquiry, or MIDI CI, which allows devices to auto-configure to work together. So when they plug in together, they can recognize what each other are. Of course, MIDI 2.0 is backward compatible with MIDI 1.0. MIDI 2.0 also features property information exchange, like product names, settings, and values, so that when you plug in an instrument to a device, it knows what it is. MIDI 2.0 also allows you to save profiles to help define how a particular device responds to MIDI messages. MIDI 2.0 also features MPE capability. MPE stands for MIDI Polyphonic Expression. It is a MIDI specification that allows electronic instruments to provide a greater level of expressiveness. MPE responds to key pressure and position on the key. Over here on the right are a series of MIDI controllers that utilize MIDI 2.0. The Rolly C-board is a famous example because it uses rubber keypads that allow you to rock your finger between keys to create a continuum of pitch, and to rock your finger up or down on the key to change timbre at the same time. This creates a three-dimensional way in which we can be expressive and change sound in real time. At the bottom is the Keith McMillan K-board, which is the next generation of the Q Nexus. The Q Nexus is the next generation of the Keith McMillan K-board, which is a MIDI 2.0 device, been updated to be it's updated to be useful in an MPE kind of way. You can press on a key, you can move your finger up or down on the key pads to change the timbre. You could rock your finger left or right to change the pitch, or any other assignable function in a DAW. Finally, we can talk about MIDI files. MIDI files are quite useful. They are an efficient way to store MIDI information only. As we know, when we use a DAW, we create a proprietary or project file that DAW opens and relies upon. When we want to create an audio file, we bounce or print to an MP3 or WAV file. MIDI files are different. Although they are not proprietary, they are meant to save only MIDI control data. Once we create a MIDI sequence in a DAW, add effects and automation, and master the project with a virtual mixer, we can then export an audio file in the same manner as before. We can bounce or print the project to audio. However, we can also export a MIDI file, or a file that stores MIDI information only and not sounds. MIDI files with an extension of .mid are universal and can be opened in any DAW or sequencer. They are also much smaller than any audio file, since it's simply a string of text. You can import MIDI files into a sequencer, music notation program, or any other MIDI-compatible program. MIDI files allow you to transfer sequences from notation file to sequencer, or to DAW, and vice versa. They allow you to work with transcriptions of famous songs. I know there's a lot of places online where you can download MIDI files of famous songs or songs from video games and other things that you can then put into a sequencer and reorchestrate. It's a very useful way to work with MIDI data in a universal way. We should know that there are two types of MIDI files. MIDI file type 0 is created so that all parts are merged into one list of events. So for instance, if you have 5 or 6 different tracks of MIDI events, all of those MIDI events are merged into one universal MIDI track. when you open it into another application, all of that MIDI information is in one track. MIDI file type 1 creates a file where all parts are separated into separate lists or tracks. So for instance, all of those 6 tracks will be saved in a way where if you reopen it in another application, the other application will honor those different tracks. Often when we export a MIDI file, we have the option to choose whether we want type 0 or type 1. Type 0 might be useful if you have 2 layers of piano score in 2 different tracks, or perhaps in a MUS score file, you have a keyboard layout with a grand staff. Type 0 will summarize all of that content into one data stream in one track. MIDI files are very useful, and it's important that we know that we can export any DAW session or sequence as a MIDI file.